All righty. So let me share my screen here. Yes, on my laptop first. There is a bunch of stuff out on the module for this week. And so let's just take this step by step. This is a quiz I'm going to go over. I've got one more question I want to do on the momentum equation, which we'll start with. Then we're going to move into chapter 7. So I've posted the chapter 7 notes and the videos for these first few sections. I suspect you got notified by Canvas that these were posted, and hopefully you looked at them. If not, you can look at them over the weekend. I've also posted a video, the dates here that under the virtual lectures. The Monday 25 October was my lecture from Berlin, and with the handwritten notes that I took. And then this is my lecture from last Wednesday. This is a video of my lecture if you want to go back over it with my handwritten notes. So there's a section here for virtual lectures. These are the past quizzes that we've already done. Or I'm sorry, these are the videos for chapter 6, but these are the past quizzes down here. And these are the things that you've got that are due coming up. I'm actually going to hide this and remove this because I've actually turned this into a bona fide assignment now. So you've got 2 assignments coming up. Your homework assignment is due on Wednesday. You've got 6 momentum equation problems to do over the weekend, and to start over the weekend. And then if you have any questions, you can see me on Monday during my office hours, or if you have questions that you think might be applicable to the class, you can ask in class too. And then also your design problem is coming up a week from today. So let's get going. I'm going to do this quiz problem. There should be no, I decided not to have a password to get into it or a code. So you should just be able to get into this. And I just want to do one more problem. And I'm going to just take a second and switch over to the iPad. So stand by. Share my screen from here. Share content, screen. Start broadcast. 3, 2, 1. Go to Notability here. Maybe? Yes. So this is my stuff from last time. And this should be, that's that. And yeah, this is what I want to start with. So if I you guys should be seeing this problem in your notes. I'm going to kind of keep an eye on the chat window too. But if I'm missing something on the chat and you want to get a hold of me, just make sure you speak up. It'd be fine to interrupt me. So let's just do this problem. It's going to be a momentum problem because we're asking about forces in this problem. We know that we need to use the momentum equation, because the momentum equation is an equation that tells us about forces, really, the rate of change of momentum. And so if we just write it down one last time here, or one more time, let's see. Summation of the sum of the external forces is going to equal the sum of all the control surfaces over the control surfaces of the outflow of momentum minus the sum of the control surfaces of the inflow. So outflow minus inflow of momentum. And we know that when the problem asks us for forces, that we are going to use this equation because the forces end up showing up over here. So we have a hot gas stream that enters a uniform. Over here, we can see that we have a hot gas stream entering a uniform diameter return bend as shown. Now, this is important, the fact that it's a uniform diameter, because that means that we're not going to have any necking down of the, we're not going to have any increased velocity, if you will. At least due to the pipe. This is a kind of a tricky problem because the velocity does change for another reason. But in any case, we have a hot stream of gas entering here at 100 feet per second, and it's coming into this bend. But what we have here is a water spray, which is changing the temperature and the density of the fluid, which is going to change. Since the density is changing, the mass flow rate changes. Because if you remember, the mass flow rate m dot is equal to the density times the volumetric flow rate. So so if the density changes in this tube, we're going to have a mass flow rate change, which is going to affect the right-hand side of the equation here, where we have the mass flows or the momentum flows. So the entrance velocity is 100 feet per second. The gas density as it enters here is 0.02 pound force per cubic foot. We're going to convert this again to slugs per cubic foot to use traditional units. And the mass flow rate is 1 lbm per second. The water is sprayed into this duct in this area right here to cool the gas down. The gas exits with a different density. It actually has a higher density because it's been cooled, and it's now 0.06 pound force per cubic foot. And the mass flow of the water into the gas. So as we inject the water into this gas, we're going to neglect that the weight of that water, the mass of that water. Perhaps there might be a scrubber in here that's accumulating the water. Maybe there's a drain for the water or something out of here, but we're not going to account for that mass of that water. Maybe it's a small amount, but for whatever reason, we're going to neglect it. The pressure forces at the entrance and the exit are the same. Now, I wanted to take this opportunity to talk about this because, and they're equal to atmospheric in this particular example. So they're just shooting gas into this at atmospheric pressure. It's going through this sprayer that's cooling it down, changing its density, and then it's coming out. So it's, in actuality, it's a pretty easy problem. Hold on just one second. I want to see. Yeah, we're good. Okay. So in actuality, it's a pretty simple problem because there's no pressure at either of the ends of the tube because of it's at atmospheric. Now, I did want to talk about this, though, that in these types of problems where you have bends, let me grab a different pen here. Oh, this one will be all right, black. That if this was a pressured pipe, let's just say this was pressurized and this pipe extended back this way, like this, and it was pressurized, we would need to have these as being control surfaces. And I want to make the point that the pressures are always compressive. So if this problem called for a closed tube like this, we would have a pressure force here. If this is 0.1 and 0.2, we would have a P1A1 pressure force here. That's compressive. And we would have a similar force down here in the same direction of P2A2. So whenever you have a closed pipe or a closed pipe that has a bend in it, you have to have these compressive forces, which are basically the pressure of the fluid, in this case a gas, times the area of the tube. So let me just back all this stuff out, because this isn't the problem that we're dealing with, but I just wanted to make that point. Let me also just draw another pipe over here. You're gonna have a pipe in your homework, and we'll talk about that in just a minute after I get done with this example. But you're gonna have a pipe with a bracket here and here, and you're asked to determine the forces on the brackets. Now this pipe is closed. If this is true, and you draw a control surface here around this, then you will have to deal with these forces. You will have P2A2, if this is 0.2 and 0.1, you will have these pressure forces in these locations. So in this particular problem, we don't need to deal with it, because the pressures are equal to atmospheric. But in a situation like this one over here, if it's a closed pipe, you have to account for these as external forces. So please make a point of that, or a note of that. Now let's get rid of this thing here. Whoops, my bad, 1 second. And then get rid of these guys. Whoops. Okay, so back to our problem. So in this case, we have if we're going to want to draw a control surface on this, or a control volume on this. So let's go ahead and choose a red pen. And we can really choose it anywhere. I guess it makes most sense to just draw it right along this. Doesn't matter a whole lot. I'm just trying to trace out the pattern of the U-shaped thing here. But we're trying to figure out what the force on that control volume is. So we know we're going to have a force in the f of x direction. It could be placed anywhere on the control volume as long as it's in this x direction. So I'm just going to place it here, which is kind of the traditional place to put it, f of x. And we're trying to figure out that force. That's going to be what we're solving for. And so I'm going to scroll this up. And so on the left-hand side of the equation is f of x. This is just kind of allowing, you know, for the fluid to have a force on the fluid, on the pipe, on the U shape. And we're going to have basically across the outflow, we're going to basically take the outflow minus the sum of the inflows. And in this case, whoops, sorry. That's an I. In this case, there's only one of them, so it's really just m dot o VO, that's a dot, minus m dot in VI. Okay, and so we need to find a few things. We need to find the velocity coming out, and we'll label this as being, you know, surface 1, and this is being surface 2, or the 1 is the inflow, 2 is the outflow, as you can see from the vector going in, basically the velocity. Now we know that V in equals 100 feet per second, and so we would like to find the output velocity. We also know from the statement of the problem that the mass flow rate through the whole system is equal to this 1 lbm per second, and we can change that to be, just 1 second, I want to verify this. Yeah, we can change this into slugs, which is the appropriate unit. by just dividing this by, we did this before, 32.2 slugs. I'm sorry, that's wrong. Let's see, flip that. We're going to have one slug is going to be 32.2 lbm. That's the conversion we need so that we basically divide 1 by 32.2 and we get 0.0311 slugs per second. So that's our mass flow rate. Now, one of the things I want to note is that mass flow rate is not going to change. Even though the density changes, that's going to change our velocity, but m dot is the same throughout the whole system. So that means that we can replace these things with m dot. So we now have, if I go to the next page, we now have f of x equals m dot times the outlet velocity minus the inlet velocity. And so all that's remaining to do is to find what the outward velocity is. And how would we do that? I wish this was a little bit more interactive so I could ask you, but think about it for a second. How have we been finding a second velocity when we were given another velocity? We've been using the continuity equation is what we've been doing. And so there's a couple of ways that we can do this, knowing, okay, so use the continuity equation. We're using the continuity equation. We're going to have then m dot in equals m dot out. And that's going to tell us that the inlet, actually that's row 1 because it has a different density. This is a case where we actually have a different density. Now, these can be ones or ins, I guess. Remember that the inlet is number 1 and the outlet is number 2. So this is just row 2, A2, V2. And these are rows, not P's. The other thing to note is that we are given the densities. And so row 1 is given as 0.002 lbm per cubic feet. And again, we can use that same, we can basically divide this by 32.2 to put it into slugs. And that gives us a smaller number, but whoops, sorry. Just want to make sure I get this right. And this should be slug per cubic foot. And we were given that row 2 equals 0.06 lbm per cubic feet. And if we convert that to slugs, we get 0. It's basically 3 times larger than this number. So 0.0182. I'm sorry, 186. And 00186 slug per cubic feet. So now we've got everything we need, and we also, we haven't listed everything we need. One of the things we need is to note that A1 equals A2. So that in our problem here, the diameter, it's a uniform diameter, return bend. So the areas are equal, but the densities are changing. And this is what makes this problem new, is that we have used that water spray to cool the air down, and it's basically raised the density. So think about this just for a second. If we raise the density of this fluid, what is going to happen to the velocity? So we know at this point, the A's cancel from this equation because they're equal. It's an equal diameter. And we have row 1 V1 equals row 2 V2. And we know that row 2 is greater than row 1. So what should we expect the velocity at V2 to be? because the density is increasing, we're going to actually expect V2 to be less than V1. So let's do that calculation. If we calculate V2 as being rho 1 over rho 2, we can see that the larger number is going to be in the denominator here. So it's looking good. And we're going to multiply that by V1. So this is just going to be equal to, I'm going to squeeze it in here, 0.02 slugs per cubic feet, 0.0. I take that back. It's these values, 0.000621 over 0.00186, and these are both
Does it
slugs.
really matter? Can you just use that ratio and just stick with that?
I could, yep. Now that I realize it, yep, I could have, because the 32 point, yep, I did not have to convert them because, yep, you're absolutely right. Now that I'm deep into this, they're both going to be a third. Very good. Thank you. And that's a third times 100 feet per second. And so it's a third of that. And in fact, it is 33.1 or 33.3 feet per second. So now it's a super easy to find the force, because we're just going to take that m dot, which is 0.0311, which is constant through the whole system, and just take the difference of the velocities. But note, in what direction is the velocity? V2. V2 is in this direction. V1 is in this direction. So V2 is actually in the negative X direction. So you need to be very, very careful with your signs here, because what you have is a 33.3 feet per second here. And then you're subtracting the inflow, and you're going to get an even larger negative number. So the signs again are tricky. And what you get is that f of x is equal to minus, if you multiply this out, minus 4.15 lbf. Because again, a foot per second squared times a slug is an lbf. And the force that the bracket, in order to keep the bracket in place, you have to have this force in the negative direction, because the gas is pushing basically in this direction on the bracket. Okay, I will send these to you. I'll save these notes and post them again. Let's see, I've got, it's 1:30, I'm sorry. Yeah, it's 1:34. Unless there are any questions on this, what I'd like to do is move on to chapter 7 and do a little bit of introductory stuff. I did want to do one thing though. It's going to take me a little second to share my screen. I did want to mention, shoot, I didn't send this back to myself. I'll just have to use my cursor for this. I did want to show you some and give you some hints for the homework for the weekend. So let me show my screen on my laptop. 1 second. Let me find my.
Really quick. So for that last question, do you want us to be typing in negative 4.15 lbf?
Yeah, go ahead and enter that. Yep. And
Okay.
I forgot to tell you that I also, for everybody that was in class on Wednesday, I went through and I just entered 2 points for everyone. So if you look at your score, you should have gotten full credit if you had tried and were there. So if there's any issue with that answer and it doesn't show up right, you'll eventually get credit. So So hang with me. Yeah, thanks. So again, negative 4.15, but with no units as normal. Okay, now hopefully, are you guys seeing this screen? Are you seeing the homework assignment?
Yeah, we got you.
Okay, so you've got some basic kind of jet problems. You've got 2 jet problems to deal with, and then you have a bend. Now remember that this. Oh, okay, so let's just take this step by step. One of the very, very difficult things about momentum problems is knowing when to apply this pressure force. And open jets do not require that, because you're going to always choose this to be 0 gauge or atmospheric. So in this problem, you have no pressure force. And you have no inlet. Basically, this one's just going to, the force on this balloon is going to be due to the outflow of mass flow rate. This one is a hose and a nozzle that's ejecting water or some fluid out, and it's hitting a window. It's a fire hose hitting a window, and you're supposed to see what the force is on that window, because fire hoses they do emit enough momentum and force to break windows. And so you're going to be addressing that issue. But again, this outlet at the is basically, and this whole control volume here that you will draw, the mass flow rate in and the out are all at atmospheric. So no internal pressure forces, or no external pressure forces. Same with this. You've got a free jet coming in at atmospheric, going around, being bent in a strange direction here. So the geometry is a little difficult, but again, so you're going to be dealing with vectors here, but no external pressure forces. Now in this one, a nozzle, when you draw your control volume around this bracket or at this bracket and then out to this nozzle, you will have a single external pressure force at 0.1. And that force will be directed from left to right, and it will be P1 times the area of this pipe, because there's pressure in this fluid and it's not at atmospheric. Out here at 0.2, as this nozzle exits into the atmosphere, you won't have that pressure force. So you're only going to have an external force of P1A1 acting from left to right onto the control volume in this problem. This problem is a closed pipe. It isn't at atmospheric. The water or the fluid is coming in from left to right and going around and exiting here, but it's closed, and therefore the gauge pressure throughout this pipe is 300 kPa, kilopascals. So if you draw your control volume to include these brackets, and can you see my cursor?
Yes.
Great. So this is probably what you want to choose your control volume to be. Now let's take a quick look at what the compressive pressure forces are. In this case, you're going to have a pressure force from left to right. That's P1. If this is 0.1, this is going to be P1A1. But here, you're going to have a compressive force that is P2A2. That's going to be directed in the positive Y direction because it's compressive. It's that's a very difficult conceptual thing to understand, but you've got a pressure force pushing in here and another one pushing in here. P1A1 here, P2A1 from bottom up into this control volume. So be careful with these pressure forces and think about the external forces and how to apply them. In this case, it's the same situation. This is a complicated situation with a nozzle with a bend. But again, just trust the momentum equation and write it out and realize what your forces are. And in this case, the control volume's likely going to be drawn here, but only one of these surfaces. If this is surface 1 and this is surface 2, this is an atmospheric. It's a jet it's a free jet at this point. So this will be at 0 gauge, but this one will have a force in the vertical direction from the bottom to the going upward of P1A1. Okay, so that should help you get going on these problems and to deal with the pressure forces correctly on those problems. And again, get a start on this over the weekend and let me know if you have any questions. Okay. I am going to switch back because I've got my notes. So just hang tight here 1 second. I need to share my screen on the laptop. Maybe it's one extra step I always need to do. Okay, and then I'm just gonna start with this. So you should be seeing the lecture notes in Notable on the laptop here, and I just did this so that I can use this pen. It's pretty nice actually. So let's go ahead and just start on chapter 7 if there are no questions. I don't see anything in the chat, so I think we're good. And these in the remaining time this week for class at last 15 minutes here, these are pretty easy concepts until we get to the derivation of the energy equation, which is extremely complex. And I would refer you to my online lecture for that. I'm going to maybe gloss over that pretty quickly if I get that far today, but let's just see how far we get. So we're going to do the final application of the Reynolds transport theorem, and we're going to talk about energy and how we can use the Reynolds transport theorem to understand how energy is transported within a system. We're going to be doing a very similar type of issue where we define a control volume with control surfaces, and we define how basically pressure and energy are kind of flowing through the system. This is going to allow us to add pumps to add energy into a system and to put turbines and extract energy from the system. So it's a very, very useful thing. So in this chapter, we're going to just, in the first section, we're going to just look at what the meaning of energy, work, and power. We need some definitions. Energy and work actually have the same units, and power is the rate of energy usage, but we'll get to that in a second. There are different types of energy. We're basically dealing with mechanical energy here, either kinetic or potential energy against gravitational energy, but there are other forms. We're going to define what a pump and a turbine are, and then just really briefly explain conservation of energy for a closed system and a control volume, and what this is really going to lead us to. This should kind of be familiar. This is going to be, this is going to kind of lead us into the discussion of the Reynolds, of how we would apply the Reynolds transport theorem to energy. Just like we did with conservation of mass, we're going to use it for conservation of energy, although it's going to be the derivation is super complex, but the application of it basically is the Bernoulli equation with some things tacked onto it with pumps and turbines. So it's not too bad with a few little wrinkles. And so then this becomes a pretty difficult section. I'll warn you right now. I would, like I said, if I get to that today, I'll say some things about it. But for the details, I would refer you to the book and also to my lecture. But we might get through some of it. So what is energy? It's a property of a system that characterizes the amount of work that a system can do on its environment. And so some examples are the water behind a dam. It has potential energy, and that water can spill through a spillway at the bottom of the dam and turn a turbine, which can provide electricity. The wind passing across the blades of a windmill carries with it force. The mass of the air can make the blades of the windmill turn aerodynamically and also produce electricity. Now, gasoline, on the other hand, used by a combustion engine, is really chemical energy. So these are forms of mechanical energy up here, and gravitational and kinetic, really. And this is really chemical energy. We're really breaking the bonds of the gasoline and using that to drive a piston. So you probably have seen this before, that units of energy are basically a force times the distance, and the SI unit is a 1 Newton times a meter is a joule. Joule is a guy's name who figured this stuff out. The traditional unit of energy, one of the traditional units, is the calorie. Now, you need to be careful when you're using calories, because there's a difference between a little c and a large c. This is the calorie that we see on our food. So, if we eat 2,000 calories a day, that's going to be calories with a capital C. And the energy calories are going to have to be, they're going to be 1,000 more of those. So you can see that there's a factor of 1,000 between these two. So be careful when you're writing, if you're going to do these, to use the C in the proper way. This is an energy calorie, and this is a food calorie. And I don't really know the history behind why those are different. I don't know why that is. It seems silly. The other kind of normal traditional unit that you might see on your energy bill in the US is a BTU, which stands for British Thermal Unit. And there are conversion factors that you can find between joules, BTUs, and calories of any type. And again, this is just a restatement. This is primarily what we're going to be talking about, is mechanical energy. Although there are other types, and also, using mechanical energy to extract electrical energy. We'll kind of get into that, or we'll imply that that for instance, a dam can produce electricity, or a windmill, or some of the different types of problems you might encounter will be converting mechanical energy to electrical energy. It's a very common thing that we like to use mechanical energy for. And so work is a form of it is energy, and work is done on a system when a force acts on the system over a given distance. So work just becomes basically force times distance. But if you have a complicated path upon which a force is acting, you need to take a little element of that path, and you need to integrate the force along it. So at any given place, it's going to be F dot ds, and you need to integrate from S1 to S2 to along that path to understand what energy was used. Now, let me just get rid of this. A better example is this. A better example is going, basically lifting something from S1 to S2, where we know that this is, we're lifting something against gravity. So mg is the force, and if this height is z, then we're raising the mechanical, we're doing work to lift this mass from this point up to this point. We're basically going to do this amount of work, which is against the potential energy of gravity. So here are some other examples that come from the book. A spray bottle. A spray bottle has this little gizmo in it that will that has a piston that's basically a pump, and it will draw fluid up into this and expel it out the spray nozzle. And so this pump, the action of your finger on that bottle is exercising this pump, which draws the liquid out of the bottle. So basically the Wheaties that you ate this morning, when you squeeze that bottle, are going into creating that pumping action, which is actually raising the mechanical energy to have the spray. And another example is when coming into a turbine and turning the blades, as I mentioned before. Both, and this could be used to create some electricity down here. Now, power, as I mentioned, is the quantity of work per time, and so this can really be kind of written as d in the limit dw dt. It's really, it can, as delta t goes to 0, this would become a differential. So this power becomes the rate of that energy is or the work or energy is consumed. This notation of w dot is going to be important because this shows up in the derivation of the energy equation. There are a number of terms that are going to have dots over them. And what that means is that that's a time derivative. Whoops, I don't know why that happened. Okay, so don't know how to get rid of that. Just a second. Okay, I'll just leave it there. We're just about done anyway. Okay, now it won't move. 1 second. Let's get back into it. There we go. And so power can come in different forms. And you can see that if it's what's called rectilinear motion, if the force is constant along that, we know that we have F delta X or delta S in our notation before. This was an S. But if the force is constant along a path, for instance, gravity, mg, then we have basically, this is going to turn out to be F times dx dt as this goes to an infinitesimal thing, and dx dt is the velocity. So that's why we see here that the power in rectilinear motion, or just kind of mechanical movement, or linear movement, is force times velocity. So this v is not volume; it's force times velocity. And then finally, you can have kind of the counterpart of this is angular motion, where you have a torque and an angular velocity, where this angular velocity is d, it is basically a change in angle as you turn something in per time. Okay, so those are, power is going to come up, and in particular, you're going to see this w dot in the equations for the derivation, as well as some other dots like q dot and other terms. And just a couple other derivations here. A turbine we're going to see is going to be a machine used to extract energy from a flowing fluid, whereas a pump is going to provide energy to a fluid. So you're going to see these two terms when we finally get done with the derivation of the energy equation. You're going to see that the pumps and the turbines are going to be on opposite sides of the equation, because in one case, the pump is going to be putting energy into the system, and in the other case, the turbine is going to take it out. So one thing, let's just go through conservation of energy, and then we'll cut it off for this week, and I'll see you in class on Monday. But conservation of energy, you've heard about before, I'm sure, and it is that basically that the energy of a closed system can only be changed in two ways. And what are they? They're by heat exchange, in or out, or by work. And these concepts are going to be seen in the derivation. They're going to be used in the derivation of the energy equation. And so note that energy is a property of the system, whereas work and heat transfer are interactions that occur at the system boundaries. So what does this remind you of? Starts to look a lot like the momentum equation, where we had external forces acting on a control volume, where we might have work and heat transfer acting on a control volume when we're considering energy. And so if you have, for instance, a system here, which is this box, whatever it is, it might contain a gas, or it might contain water, it might contain gasoline. You're going to have an amount of energy that's in that system at any given time, and you're going to have the ability to have energy enter the system either by doing work on it, say by a pump, or by transferring heat into it. Whereas you're going to be able to extract energy out of the system by allowing it to do work for you, like a turbine, moving a turbine, or by also having heat transfer. So this is really these concepts that we've gone through today, all these definitions, and the definition of energy and power, and then what a pump and a turbine are, and then also conservation of energy, and leading up to this concept here. These are basically going to show up in this derivation of the energy equation, which is basically the Reynolds transport theorem applied to energy. So the law of thermodynamics says that there needs to be a balance of work and energy. It says that any increase in the energy stored in a closed system and the rate of change of that energy, well, let me just take one step back, and then we'll finish up. The increase in energy stored in the system is going to be equal to the amount of energy that entered the system by heat transfer minus the amount of work left to do work. That is a definition of the law of thermodynamics. When you take the time rate of change of that, when you take it with respect to the derivative with respect to time, you get dE dt, the change in energy per time, is going to equal Q dot minus QW. This is for a closed system. So this is looking a lot like the left-hand side of the Reynolds transport theorem. And so when we meet next time, you will see that when we write down the Reynolds transport theorem, this is going to be the left-hand side, and this is going to be basically the flow of energy out and the flow of energy in. Okay. And so we will pick that up on Monday. Any questions? It's Friday. All righty. Again, thank you guys. Thank you for safe travels, Adam. Yep, I'm leaving tomorrow morning. I'll be home at midnight tomorrow night, and I will definitely see you guys. You guys also have a great weekend. I don't know what the weather's like back there, but it was beautiful here today. And again, thank you for enduring this. It should have been recorded. I'll post the recording hopefully before I take off tomorrow morning, and you can look at it over the weekend again if you need it. Thank you, and we will see you guys soon. Take care. Have a good weekend.